So, hello everyone. Now it's time of the last presentation of today. That would be also the last presentation of this workshop. The presentation will be in charge of Marcelo Colominas. After starting with his talk, I will say some words about Marcelo's career. Marcelo Colominas received the engineer degree from the Universidad Nacional de Entre Ríos in 2011, receiving the Best Graduate Award of the Argentinian National Academy of Engineering. He received the PhD degree in engineering by the Universidad Nacional del Litoral in 2016. He was a postdoctoral fellow with the University of Angers in France from 2017 to 2018. He joined the Department of Mathematics here in the Facultad of Ingeniería from the Universidad Nacional de Entre Ríos in 2008 and became a teaching assistant in 2011 and later adjunct professor in 2019. Also in 2019, he joined the Consejo Nacional de Investigaciones Científicas y Técnicas here in Argentina as an assistant researcher, and since 2022, he has become an adjunct researcher in the same institution. In 2021, he was a Fulbright visiting scholar at Duke University in USA and also a visiting professor at Université Grenoble-Alpes in France. His research interests include time frequency and time scale signal analysis, Synchrosqueezing, data-driven methods, and biomedical signal processing. So, Professor Colominas, the room is yours.
Thank you very much. Thank you very much, Gabriel, for the introduction. Okay, this talk will be mainly motivated by some specific features encountered in some biomedical signals. I wouldn't say all of them, but a good group of signals or set of signals. A lot of signals do have some of these properties, some of these characteristics, and this wave shape function model was mainly motivated by them, and I will try to explain what this model is about and some generalizations and some improvements. But we will start with a typical biomedical signal. This is an arterial blood pressure signal. And the things that we want to observe here, well, there are many things. Well, we can see that it has a trend, but maybe more importantly, we can see that it is amplitude modulated in the fact that the amplitude is far from being a constant. For instance, here, a peak-to-peak amplitude is about 53 millimeters of mercury, and here it's 59.5 millimeters of actually quicksilver. Mercury is the planet, I think. Okay. And also, they are frequency modulated. It means that the frequency changes with time. We can see here that this distance is 708 milliseconds, while this one is 620. So we have a trend. Normally we have noise, although this example, the content of noise is not very important, but we normally have noise. Trend, we have modulation in amplitude and modulation in frequency. Those are characteristics that we can encounter in most of these non-stationary biomedical signals. But the point here, which is something that I will develop through the talk, is that there is an extra feature in the sense that the waveform changes. There is this pattern of oscillation that could be quite constant, but it can present slight changes, but it can also present sudden changes that we will see later. Here we have the 4th poles, okay, and the 40th poles. Even though, okay, they might be similar, they are actually different, and we will try to model that difference and try to explain in terms of the observation why they are different. Okay? We will be discussing some models, but not models of how these signals are models of production, I would say. No, it is not about how these signals are generated. No. But we will model the observations. Okay, we will have a phenomenological model about the observations that we can record with any device. So the example of the arterial blood pressure, where we can, for instance, be interested in describing this waveform change, which in the previous case was kind of like a slight change, but here we have a sudden change. Okay, this is an ECG signal. We can see here in milliseconds the distance between two QRS complexes, meaning that, of course, the frequency is far from being constant. And here what we have is an ST segment, okay, between the two red crosses. So we have a fair normal signal in black, except for this event here. But then in red, we can see that the ST segment is elevated, which is normally a marker of myocardial infarction. So what we can see here is that the waveform evidently had changed, and it changed I would say, in a sudden manner. So we will try to see what we can say about these kind of signals, how we can characterize them. Okay? And a final example for the motivation is this impedance pneumography signal, okay, where the goal of this signal is recording respiratory activity, and we can see here inspiration and expiration. But what we are seeing with the blue arrows are cardiogenic artifacts. So for these kind of signals, we might be interested in a decomposition task. Okay, while for the first one, we can be interested because we consider it as a single component. We can be interested in characterizing that signal and maybe do some form of segmentation to separate these two evidently different waveforms. Here, maybe we are interested in decomposing this recorded signal into a respiratory component and a cardiogenic component. So we'll try to see different ways to model these signals and to perform tasks such as decomposition, denoising, or segmentation using the wave-shape function model. Okay? Okay. Yeah. Just to summarize this motivation, we will encounter that the non-stationary biomedical signals are amplitude modulated. They are frequency modulated. Normally, they have noise and trend. Normally, some of them are present in our recordings. And we have a waveform that we will call the wave-shape function that changes with time. In most cases, okay? Okay, this is an example from a publication of mine and Hao Tian book, that we took this example as a motivation. We'll start with this idea of wave-shape function. What do we mean by wave-shape function? How can we model that, and how can we use for this? How can we use them for these different tasks? Okay? We have here, of course, a simulated artificial signal. But what we can observe from here is there is an oscillatory pattern that repeats itself. But this signal is far from being periodical. Okay? It is modulated in amplitude. I don't know if you can see that we have these. Okay? Here we have a modulation in amplitude. And of course, this oscillatory pattern is stretched or compressed because of the modulation in frequency. Here at the middle, okay, the waveform has a longer duration, and here we can say that the signal oscillates faster than in the middle section. So The idea is to see this signal and to model it like this. In a generalization of a classical AM/FM signal, where in that case we have a cosine that is modulated in frequency and in amplitude. Here, what is modulated in frequency and amplitude is a function S that we will estimate later. Okay, so S is this oscillatory pattern that repeats itself, being stretched or compressed by this phi, which is the phase function, phi prime, the derivative being the instantaneous frequency, and maybe scaled in amplitude by this A of t function. Okay? So this is the idea, this is how we model these types of signals. Gracias. So normally we impose some constraints on this model in order to have a physical meaning and to be identifiable. For instance, okay, we want the amplitude to be non-negative function, okay? And also we want the derivative of the logarithm, actually the absolute value of the derivative of the logarithm, to be bounded, normally with a small epsilon, okay? And we want the instantaneous frequency to be positive, okay? With the second derivative also normally bounded, okay? Normally in the terms of usually bounded, okay? And finally, we will have this wave-shape function, which, as I said, it replaces the cosine function in a classical AM/FM oscillation, but we will describe it as a 2-pi periodic function. Okay? And as a periodic function, it will have a representation as a Fourier series, where these S hat are the Fourier coefficients. Okay? And some properties about this coefficient is that, okay, there exists a real number delta such that all of the modulus of the coefficients are bounded by some multiple of the first one, okay? And, okay, there exists some d and some theta such that this sum converges. This means that these coefficients decay faster than 1 over n squared. Actually, they have to decay as 1 over n cubed or faster, you know. That is what it means. It means that we do not have coefficients that do not decay. And because of this property, the wave-shape function will accept a bounded bandwidth approximation. Okay? We will see about that later. Okay. So we have this where we just replace the function S by its Fourier series. And since the function S is evaluated at 2 pi phi, we write here 2 pi phi. Okay? And, well, we can use the real form of the Fourier series to write this as a function of alpha and beta. Now we have real coefficients here and only positive frequencies. Okay, we are all agree on that. And we can also write it in this way. It's the same thing where there is a direct mapping between alpha and beta to A and B. Okay, no problem about that so far. And what we will do, as I said, we will approximate this instead of with infinite number of harmonics. We will use just D, because we are sure that after D we are not losing too much information because of this fast decay of the coefficients. That's the idea, and we will say something about this D. Okay, but now how do we solve the wave-shape function model, and what does it mean to solve? What to solve is to estimate D somehow and to estimate the coefficients that will allow us to characterize this wave-shaped function, to characterize this oscillatory repeating pattern, even though the signal is not periodical, of course. Yeah. Okay, so we can estimate the amplitude from the STFT, for instance. Okay, this is something that people normally do without any problem. And we can estimate also the phase using the STFT or the Synchrosqueezing transfer, the second order or the higher order. Okay, Sylvain showed us some very robust algorithms to detect the ridges, and also if we are able to detect the ridge, we are able to detect real value estimations of the instantaneous frequency, for instance, using Synchrosqueezing operators. Then we can do two different things. Either we reconstruct the mode around the ridge and take the phase of that complex number that would give me the phase, or we can just integrate the instantaneous frequency and there will be no problem about the constant of integration. Okay, I can just assume the integration constant is 0, and we will be able to solve that issue, because we will in the discrete time setting, we will construct this matrix C. Okay, it would be like kind of like a dictionary for the signal, where we will estimate, we will have in the rows, we will have these AM/FM cosines and this amplitude and frequency modulated sines. Okay? And then, if we consider our observation that is written as certain coefficient times this matrix plus some residue, which we can assume it is not correlated with the information of the signal, then we can solve this optimization problem in a classical way. In a classical way where we have these normal equations that will give us the coefficients A. Okay? Provided the residue and these rows are not correlated. Okay? And then we can, of course, reconstruct our signal at those discrete time points, just as this vector A tilde, okay, times the same matrix. That is the general idea here. But the good point is that, okay, we know how to do this, we know how to do that, okay? So we construct the matrix C, kind of like a dictionary, only that is a direct projection onto that pseudo-Fourier dictionary, because these are amplitude modulated functions. Okay? And how to choose D? You see here I have D cosines and D sines. It should be D. It should be the little d, yeah, okay, with a big D. So, sorry for that. How to choose D? Okay, we have been working with Joaquin Ruiz, trying to adapt some well-known trigonometric regressions criteria that were used some decades ago for stationary signals, and try to adapt them into this non-stationary setup, and they work well. They work well. Simply, we can imagine that as soon as D increases, the error will decrease, of course. But if we have noise, we will be incorporating more and more noise into our coefficients and into our reconstruction. So somehow we have to penalize the model of the size in an archaic style, of course, and several options to penalize seems to work really, really well and give us a fair idea of an optimal number for D. Okay. Okay. Let's see a toy example. Okay. If we have this S of T, which is composed of 3 harmonics, and we use a 5, which is, in this case, 5 is oscillatory and also increasing. Okay, we cannot see 5 here. Okay, But let's say we can estimate it somehow, and the results are estimated from the STFT. We estimate the phase and we estimate the amplitude. But we have this clean signal. Now, I added some noise at 10 dB. No, 10 dB, no, I'm sorry, at 0 dB. This is 0 dB. Okay, this is 0 dB. Then we run the algorithm, and this is what we get. Okay, the noise here in gray, yeah, I think you can see it. The ground truth in red, and the estimation is in black for 0 dB. It is a good estimation, and I think a valuable idea of the method is that we can estimate this oscillating repeating pattern that can be useful somehow. In this case, we have a denoising mission here, but also we might be interested in characterizing this oscillatory pattern. Okay? Okay. So far, I think I hope to be clear enough about this. Of course, it can be generalized to more wave-shape functions, meaning that in the same recording we have more than one, as in the case of the impedance pneumography example, where we had the respiratory component and also the cardiogenic component. Okay, so it can be generalized to I, capital I, being any number, but normally more than 2, 3, it is difficult to encounter in practice, and it could be difficult to solve also. Okay, but we have a lot of examples with 2, the fetal ECG problem being one, where we have 2 different oscillatory patterns, and also this cardiogenic example that I showed you before. But it can be generalized, and we will do the same. We will have to estimate all the AI, all the phi I. With 2, we can do it. With 3, it can be more difficult, actually. But still, and we will have to construct all of these atoms, and then we proceed as before. We estimate a vector of coefficients A, and this, this vector can be seen as a concatenation of, of I smaller vectors, and every segment, every portion of that vector will give you the different. And we try this with 2 real with 2 components on real signal. It worked okay, and we tried with 3 on artificial signal. It worked okay, but of course it were artificial signals. Normally, I would say that more than 3 would be a difficult problem, and also very, very rare to encounter those examples. Okay, but the thing is that what I just show you is a model, very basic model, that could be useful up to a certain point, because what we assume is that we have 1 or 2, any number, but oscillatory patterns that do not change with time. Of course, they can look different only because they are stretched or compressed, or they are scaled in amplitude. But the wave-shape function does not change. They always have the same number of harmonics and the same amplitudes. And that is not very typical in most biomedical signals. So what we try to do here is try to explain somehow why are these patterns changing, and how can we model those changes. And that is why with Haukenbu we came out with this model of slowly varying wave-shape functions. I will show you an example. This is the previous example. This is a previous example. It was that, okay? We can easily write here, to open here a bracket and write cosine of 2 pi phi of t plus 1/4 cosine of 2 pi 2 phi of t, and 1/3 sine 2 pi 3 times phi of t. Okay, would be the same. What happened if instead of being all integer multiples, we can try this, okay? Very, very small departures from the integer multiples. What will happen, okay? This is what happened, you know? We have the same A of t as before, and we just change this from 2 to 2.01, from 3 to 2.98. And what we can see maybe resembles that ABP, arterial blood pressure example. Maybe it resembles. Somehow we can see we have an oscillatory pattern here which slowly evolves. This, it has two peaks here, okay? And here again, one peak, but with inflection on the right, before the inflection was on the left. So what is happening here is that this fixed wave shape function model is no longer valid because the different harmonics, and it is harmonics, you know, with like that, harmonics, not real harmonics, but in an abuse of terminology, I would still call them harmonics, but they are not because they are not exact integer multiples. But anyway, these harmonics, they are not integer multiples, and this is what is happening here. Okay? So, and this is just a comparison to the previous case where these were with those integer multiples, okay? Just a comparison, okay? So, how can we adapt this original model to reflect this phenomenon? Okay, we simply stop assuming that the fourth harmonic is 4 times phi, okay? We change this L to pi phi to 2 pi phi L. And phi L is no longer necessarily a multiple of phi, would be phi 1, okay? So we have the same conditions for A, meaning slow variation for A, meaning the derivative of the logarithm of A, that absolute value being bounded by a small number epsilon. But we no longer have a fixed S of t. We do not have that anymore, so we cannot, I mean, we can find, but it will not reflect what is happening in the signal. So in this case, the idea of an S of t makes no longer sense, okay? But what we know, it's not that we know, but most of the biomedical signals show us is that even though those harmonics are not integer multiples, even though they are not far from being a multiple, okay? So we can say that phi prime L, the difference between phi prime L and L from phi prime 1 is small, okay? It is bounded, the difference. That's the idea. I just show you 2.01, 2.98, okay? And because this difference is small, we say that the wave shape function is changing slowly, okay, because of this. So now we will not be able to estimate a single S of t because we do no longer have that, but we will be able to use this tool mostly as a decomposition tool or also a denoising tool. How do we solve this? And possibly with I components, and we did it on real signals with 2 components and on artificial signals with 3 components. Again, we can estimate the amplitudes and phases, the fundamental amplitudes and fundamental phases from the STFT, and we can consider this problem, okay? This problem, anyway, we can, for the sake of clarity, we can just imagine I capital is equal to 1, and that's it. But what we have done here compared to the previous case is we have introduced this phi L. Instead of being L times a given phi. Okay, this is the main difference here is this. And also we have to, we must find a way to model these phases, okay? And we will say that these phases has to be fitted, and also the DI should be estimated, and those trigonometric regression criteria that we study with Joaquin, they work okay, and they work for more than one oscillatory component, okay? That should not be a problem. But the phases, how do we estimate them? Well, simply because they can be something different from an integer multiple. If they can be something different than an integer multiple of the fundamental phase, we can think of a model like this in a polynomial fitting fashion, where we just, this one was estimated, okay? This one was estimated, and I will say that for L greater than 2, because here is with L equal 1, okay? It would just be, you know, something like this, a combination of this fundamental phase raised to the kth power, and that's it, okay? Normally, capital K no greater than 2 or 3 is needed, and actually for most of cases you can use capital K equal to 1, and that's it. It would just be the estimation of this non-integer coefficient. If you have capital K equal to 1, and if you have this E being an integer number, you're in the previous case. Okay. So this is the idea, and of course for L and K being 1, you just set this to 1, and that's it, because you estimate for L greater than 2. Okay, so if you do that, you have this evidently nonlinear regression problem. Again, you can imagine I to be 1, D can be estimated in a reasonable way with a good low error, and you will have to solve this optimization problem for C, D, and E. Okay, and that's the idea. So you solve this, and you will have your reconstruction with this slowly time-varying wave shape function model, of course. But this is, I mean, we cannot prove this is convex, of course. I mean, it's not convex, but it has a good optimum that it should be stable at some point, if we are now far from the assumption that the multiples are close to an integer. They have to be close to an integer, and in that case the optimum will be stable. So since it is an optimization by gradient descent, you can think about NLin fit function from MATLAB, LSQ curve fit from MATLAB, also your favorite optimizer. But the point is that, okay, it needs an initial point. This is an important step. This is a really important step. And luckily, since and because the wave shape function does not change that fast, you can use the previous solution as an initial point. So you use the previous solution, and you can be sure that that's a warm start, and that the optimum is not far from that point. But because of the non-linearity of the problem, even though the coefficient moves just a little, you could see that the waveform it changes. I mean, significantly, I would say. Okay, so you take that as an initial point for the trigonometric coefficients, and because of this property, as I would say, that the phases are not far from integer multiples, you just initiate them with integer numbers. Okay, so your first guess for the phases are just integer numbers, and that's it. And 0 for those coefficients with the power greater than 1. And you just let your optimizer to go to the solution, And you can find this on another paper with Houtian, and also the codes, they are available at GitHub. Okay. So we have here our previous example. Okay. And if we again add some noise at 0 dB, I didn't say, but this is Gaussian white noise with zero mean. If you add some noise at 0 dB, okay, then you run and you have that. Okay. Again, this is the estimation in black, the ground truth in red, and still you can see that the model, the solution, it caught all these changes with the inflection point here being on the left, here on the right, although the inflection points tends to be more like a local maximum, okay, which was not present on the signal, but still at 0 dB, I think it is a reasonable solution, and we can be happy about this solution because it reflects what we want it to reflect. Okay. 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 So let's move on right now with some examples. Just some examples. I will go fast through this. Some examples from that paper. These are simulated signals, but somehow they are similar to some signals encountered in practice. When we have a signal on the right that we can call sometimes spiky signal because we have like a fast thing here, and here some oscillatory signal, but with some local maxima. Here some peaks that actually they change. Okay. So we have here at 10 dB an example with noise of 10 dB, and we have these two components that when you add them, okay, you form a clean version of this function. Okay, and we have here the solution of we call this method shape adaptive mode decomposition, and we first compared to the previous solution that we call just LR for linear regression, because it was actually just a linear regression. What we did with the first fixed wave shape function model. Okay. Okay, I will go fast through here. You can see that these features appear here where they are not. Okay, here and also here. The solution here is, to my opinion, less satisfactory here. But anyway, it is reasonable to think that the shape adaptive mode decomposition would do better than linear regression, since actually linear regression is the initial point for this shape adaptive mode decomposition. So, I mean, of course, it will do better. But we can also compare to this RDBR method that is from Haixiao Yang and Ingrid Obeshi. Okay, they are both the authors of a paper on applied computational and harmonic analysis. And the thing is that RDBR, it takes forever to run. Actually, it takes a lot to run, and also it works on a fixed waveform idea. You can see that, okay, the waveform is fixed both for S2 and for S1, and when you compare to S2, what we have here is 100 realizations of the experiment, and you have in black you have the mean value, and you have all the results in gray. Okay, but we can also compare to the multi-resolution mode decomposition, which is the second iteration of the RDBR, but this time only from Haixiao Yang, where he tried to adapt to this change in the wave shape. Okay, again, you can see the MMD results. Well, they are not as good as ours, and it takes 1 order of magnitude more in time. Okay, a second example, again a toy example, but you have these delta-like features here. Okay, they are all of the same width, so you cannot think this as an AMFM function, because all the widths are the same, but they are separated differently. But this is closer to an ECG case where the QRS complex is not stretched or compressed. Okay, and again, much better results for shape adaptive mode decomposition. As you can see, this is the initial value, the initial point. Okay, this is the initial point used, and the algorithm goes to the correct solution. Yes, the algorithm goes, and it is a stable optimum. As you can see here, we have you know, an horizontal line here, while we have some oscillations here. Okay, the same for RDBR, and the same for MMD, that it is more or less able to follow the change of this waveform, but with much more error. Okay, you can see a lot of error here, a lot of gray behind that that curve. Okay. Finally, just a quick example on an ECG recording where we have some noise, and the amplitude of natural noise, and the amplitude of the noise here at the beginning is greater than at the end. Okay, I don't know if you can see how the amplitude of the noise is decreasing. So we have a non-stationary noise. The shape adaptive mode decomposition, okay, it works fine to my opinion, and the linear regression, as you can see, it introduced this artifact. Okay, this artifact here that was not present. Okay, here we can estimate a waveform. Okay, we can estimate, and we know exact the coefficients here. Here we cannot estimate. What we did just is just segment the signal. We use the phase of the signal, which we know, and use it to segment. So every time we move 2 pi, we cut, we move 2 pi again, we cut, because we have the phase of the signal. So we can do this, and all these cycles, they are slightly different from each other, meaning that the method was able to catch these changes. Okay, and of course, in terms of the trending and denoising, it is much better. The RDBR, similar to the linear regression, okay, linear regression, where we have something strange here. I don't know what's happening here. Okay, you can see just before the T wave. Okay, just before the T wave, we have something. Okay, and the MMD. Okay, it removed some of the noise, but it kept all the trend, maybe. Okay, it kept all the trend, and we can see here the different waves. I'm comparing all the time to SAMD. Okay, so you can check that. Okay. Okay, hope to be clear enough so far. And I don't know about the time, but since it's the last talk, maybe I can use an extra minute, some extra minutes. I'm sorry. Okay, so what we had is this at the beginning. Then we just generalize. Okay, we say, okay, the phases are no longer integer multiples. We can adapt much better to real biomedical signals, but still we only have one modulation in amplitude, meaning that the changes in the wave shape, they were only caused because of these non-integer multiples. But when you have all the harmonics, all of them were amplitude modulated in the same way. So if you want a change in your wave shape function, you have to, okay, move apart from an integer multiple that harmonic. But I call this 2.5, okay? This was an idea, again, by the group of Hautien, but they try to characterize the signals in this way with some relationship between those BL and this phi L, but they didn't come up with an algorithm to actually solve this. But they did describe mathematically this, and they came up with this D-shape STFT, which it's like a short time Kapström transform. It is really interesting, and it helps with some practical problems. And they try to characterize this. Okay, the phases are not far from an integer multiples, and all these amplitudes, time varying amplitudes, they are bounded by an L1 sequence, okay? Meaning that when L increases, the amplitudes, okay, with L for a given time, the amplitudes with L for a given time will decrease, and it will converge because it is bounded by an L1 sequence. And also the derivatives, this should be, you know, the other way. Yes, it should be the bar should be on the denominator. I'm sorry for that. Okay, I'm sorry for that. And you can find this at the Journal of Fourier Application Analysis, Siwei Lin, Zhu, and Hao Tianbu. I mean, it is very interesting, but they did come up with a method to actually solve these. And this is right now the work of Joaquin. He's trying to solve this method, trying to model these amplitudes with some splines and some specific nodes that would catch most of the information. And when you interpolate between those modes, okay, you will lose as little information as possible, okay? That's the idea. Okay, we can move forward to the last part of the talk. We can think about a third version where, again, now the variations of the wave shape function will be caused by the phases not being integral, and also by having those harmonics, different modulations in amplitude. And we will suppose that there is a dominant component. Okay, this is a dominant component. D might be different from 1, so maybe the dominant component is not the fundamental component. And we will just replace this fundamental frequency, as you can see, by the derivative of the dominant phase divided by D. Okay, so this is a new estimation of the instantaneous frequency that is given by the dominant harmonic, which might not be the fundamental harmonic. And anyway, more on that about instantaneous frequency estimation in another word that I hope to discuss with Sylvain next week. Okay. Now it is the dominant harmonic, the one that it is the dominant harmonic, the one that will be bounding the rest of the harmonics through an L1 sequence. Again, the bars go in the denominator. And here, instead of fundamental frequency, we have this dominant frequency divided by D. And the basic idea, I hope not to be too complicated right now, that there are change points. There are specific change points where this B, other than the dominant, it can change quite fast. And you can think under certain restrictions, your signal something like that. In this case, we have R plus 1 change points. This is an indicator function, and you can see that, okay, from time to time, you can have different segments with different wave shape functions, and that's the idea. They can change fast, as in the original case where the ST segment was elevated. Okay, the thing is that you will have some different waveforms for different segments of your observed signal, and okay, you want to solve this and try to estimate this Sj. Now we do have Sj. Okay, we have different wave shape functions for different times. That's the general idea of this model, and we want to solve it using iterative warping and clustering. Okay, we can suppose that D is equal 1 just for the sake of simplicity, and we estimated somehow the phase, maybe with the STFT or with Synchrosqueezing transfer, as I said before. We can warp the signal. I say warp the signal. Sometimes it can also be found as demodulate the signal, but this is different from the demodulation that Sylvain mentioned. Okay, here we are not multiplying the signal, by a complex exponential complex exponential with the phase. No, we are evaluating the recorded signal on an estimation of the inverse function of the phase. Okay? We do that. Again, in this special case, this is reduced to this. If we are able somehow to estimate this amplitude, just dividing by that amplitude would allow us to recover the Sj. How do we do that? First, we segment the signal and we cluster all those segments. Okay? I hope I will be clear enough in the next slides. Okay? We will segment the signal using the phase. We will have cycles of the signal. Each cycle might be different. And then, okay, you say, okay, you have n cycles, but out of those n cycles, they are not all different from each other. You can try to cluster. Okay, and you can see that the first 5 cycles belong to a given wave-shape function, the rest of them to a second wave-shape function. And you can say, okay, we have 2 very different oscillatory patterns in this recording. That's the idea here. That's the idea here. We want to estimate this as J. Okay. How do we do this in practice? Okay, because it looks nice on paper, but how do we do it in practice? What we do is we have to estimate the phase function, and with that estimation, we can create an estimation of the inverse of the phase, and using that, we just resample the original signal. Okay, we have the signal in discrete time, but we can always interpolate the signal in discrete time to have an approximation of that real-time signal, and we can resample that interpolated signal, okay, to have what we call the warp signal. And that's the idea here. More details on the paper we can discuss later, but if you have, originally you have a linear chirp like this, and you compute your simple FFT, you will have this gray modulus that will tell you that the frequency is quite spread, isn't it? You know, and after your warping, you have this, and it is clear that it's much more concentrated in frequency. And by doing that, what you are doing is you are killing the effect of the frequency modulation. You kill the effect of the frequency modulation. And if you previously divided your signal by the amplitude, you kill the amplitude modulation, then you kill the frequency modulation, and now you have the only source of variation of your signal is the change in the wave-shape function. So you can segment your signal after this, you segment the signal, you cluster, and you find those different oscillatory patterns present in the signal. Okay. An extra difficulty is that the estimation of the phases are never perfect, you know. So you estimate the phase, you go to the warping step, and you think you're happy. Now I will use this phase, I will segment my signal, I will cluster. No. Normally, these estimations are never perfect, but what you can do is you can iterate. Okay, now you warp your signal, still, it is not still like a constant frequency signal. You can do it again, you can do it again, and you can do it again. Okay, the problem with these iterations is that, okay, you might not have a convergence guarantee. Luckily, we do have, and also a practical criterion to stop your iterative process. But we'll see about that. Okay, we came up with some theorems. You know, this paper has a long 6 pages appendix with some theorems. Okay, that prove that actually this iterative scheme it converges. Okay, the idea is that, okay, let's try to think about this theta. Okay. If this theta is perfect, then theta is just t, because it's just the function evaluated on the inverse function. It's just t. Of course, it has an error, but what we proved in these theorems, because this is the second one, is that, okay, these errors are controlled and are bounded. And then when you do it a second time, it will be, again, possible to prove this, but with a smaller epsilon. Okay? And if the epsilon is smaller every time, it means that the process, it converges. Okay? So you have this for the phase. You want, in the end, you want this to be just t, of course, and also for the amplitudes. In the end, you want the amplitude to be 1, meaning that you kill the amplitude modulation. Okay? Of course, it is not 1, it has an error, but again, it is bounded and controlled. And the second time you do, you can prove that the second epsilon is smaller than the first one, and it will give you some guarantee. Okay? Okay, hope to be clear enough on this. How many iterations? Okay, because, okay, yes, it converges, but it can converge after 1,000 iterations. I don't know. It's not the case. We need some practical tool to measure this improvement with the iterations. We are using the SVD entropy. The SVD entropy, it is just the classical Shannon entropy, the formula of the Shannon entropy, applied to the singular values, of course, the normalized singular values of the decomposition of a matrix in which in every row you have a segment. Okay, this is an old, maybe 20 years old idea from a researcher called Alter. He comes from bioinformatics. Okay, and it was used maybe 5 years ago by Boalem Bouachache, which is a very known researcher in time frequency area. He applied there. So you can imagine, for instance, that you have a rank 1 matrix, meaning that all the rows, they are multiple to each other. Okay, it's rank 1. In that case, you will only have one singular value different from 1. Okay, you will have the smallest possible value in this SVD entropy. The opposite case, if the rows, they are very different from each other, then you will have that all of the singular values have more or less the same weight. You will have with the maximum value. And now what we are doing here is that, okay, since we are allocating the segments on the rows of a matrix, you say, okay, maybe my recording has only three different wave shapes. So you expect those rows to belong roughly to 3 clusters. Okay, 3 clusters, and within a cluster, all of them are just multiple, just multiple of a single waveform. Okay, and if you iterate, you are able to measure with this the quality of your process. I will show you later. Once the signal is warped and demodulated, you can use the phase to segment it. Okay, and how to find this, the wave shape functions? You can just cluster the segments. For instance, with k-means, we use k-means. It works okay. It is the best clustering method. I don't know. We also tried hierarchical trees, and the results were better with k-means. And even you can run simple examples, and when you have that the length of the segments is roughly the same of the amount of cycles, so you have more or less a square matrix, k-means works much, much better, and the hierarchical tree can have some errors. Okay, and then you can take the medians or the means of the cluster as the wave shape functions. If you have too much noise, you can also run trigonometric regression on those medians or means. Okay, to try to suppress some of the noise. We have here a toy example. We have an artificial signal at 0 dB in gray, and the ground truth on red. And when you run, you found this. Okay, here the ground truth is in red, and the estimations are in black. As we can see, we have some sudden changes in the here. I think we have one or two harmonics. Here we have three. Here we have 3 or 4. So the idea is that the method is able to estimate these waveforms and also to perform a denoising task. Okay, a denoising task. Okay, so right now, and don't be afraid. Just examples. We will show about more examples, and that's it. Okay, you can have a sustained vowel. This is from Saarbrücken, I think. This is sustained A vowel called low, high, low. It's la and you have your signal. Yes, STFT. You estimate the reach, and you do this warping process. And this is the STFT of the warp signal. I don't know if you can see the effect, okay? We just killed the frequency modulation, and we also killed the amplitude modulation. So this signal can be segmented using the phase. You can segment the signal, and you can collect all those segments in a matrix like this. And then you just cluster the matrix. Here's the clustering. It found class 2, class 1, class 2. In the end, 1 class 1, okay? 1 or 2 is irrelevant here, okay? And so you can see the waveforms estimate. I mean, maybe those of you that works on signal, this might not be on voice signal, this might not be surprising, you know? But when I first saw this, I expected that the high would be just the same waveform of the low just compressed because of the frequency increased. But actually, that was not the only effect. The waveform changes. So you have one waveform from the low or neutral and another waveform from the high okay? And well, you can estimate those changes. Maybe some naive example here, but anyway, you can estimate those changes. Here you can see the original. It has here this distance, here this distance. This is this part of increasing frequency, okay, from 65 to 85 here, okay? And the warp signal is almost a constant frequency signal, okay? 998, 9979, okay? Almost a constant frequency because it was an easy example, actually. No noise, very clean signal, nice structure. Here you have like some vibrato at the end, maybe, okay? But anyway, the method worked just fine. Then we just created a more challenging example, just concatenating 3 different signals. Okay, this is just concatenation. You have E, U, E, something like that. Okay. What you find here is just three different signals. You have the neutral E is the same as the low E, because when you ask the speaker, he would you say low, high, low. He would say the first E. He won't go E. No. He would say E, and neutral E. Okay. So neutral and low is the same E, and you have your U, and you have your high E here. Again, we just did the same. You can see here how this warp signal. Okay, you killed all the amplitude modulation and all the frequency modulation, okay? And you estimated the different waveforms which might be useful for different tasks, okay? Let's see some more challenging examples. Arterial blood pressure, simultaneous ECG record, and you can see an arrhythmia here, okay? You can see a double beat, then double beat. No, see? Ta-ta, ta-ta, ta-ta. And you can see that here it created a different wave shape here. This is like a regular wave on the waveform on the ABP signal. And here you have this double peak, okay? Because the pressure did not return to the resting state, okay? You have something like a refractory phenomenon here, kind of, I don't know. And this is the the original spectrogram, and you can see the reach. When you demodulate just once, you got this. Okay? Had this process been perfect, this fundamental component at warp frequency equal to 1 would have been just constant. Because of these sudden changes in these jumps and some errors in the estimation, is not still constant. But anyway, you do this, you segment, you measure the SVD entropy, and if you want, you can just cluster just to see what happened. And you will not be happy with this solution. You think, okay, the estimation of the phase was not good enough because the warping was not good enough, because this matrix is not good enough, because the SVD entropy can still decrease 2.51, 2.41 after 3 demodulations. And now the fundamental component is more constant than before, and after 5 demodulations, it's like that. Okay, 2.4, 2.38. Now the difference is not as big as before, so you can use a threshold in the difference between 2 consecutive SVD entropies as your stopping criterion. And you can see here, after 5 demodulations, you got something like this. You can cluster, you can find 4 different wave shapes, only one example for waveform number 4, so it could be something like an outlier, and you can use this to just paint your original signal, where you can see the normal or regular bit is the most frequent one, waveform number 2, and you can use this method as an indicator of atypical cycles. Okay, and those cycles in blue are the one related to arrhythmia. Okay, you have this black, is the waveform number 4, appear only once. Something strange there, huh? Nothing strange. And this magenta color, okay, could be a mistake between waveform number 1 and waveform number 2, that the algorithm, it found a cluster that it wasn't supposed to be there. We are not sure, but still, it is good enough for segmenting the signal. It can happen that something like that for the ECG, the dominant harmonic is not the fundamental. Okay, that might happen. It's a very interesting case when the dominant harmonic is not the fundamental. If you demodulate with the first harmonic, which is the fundamental, you found this. I don't like this matrix because a lot of shifting and the SVD entropy is high. If instead of using the fundamental, you use the second one, you find something like this, which is better, but still you have some shifting. So you can correct that. You say, okay, I use the second one. Now I have my phase is twice as the fundamental, okay? Kind of twice. So I want to divide it by 2 to segment the signal. Okay, if you do that, you will end up with this segmentation. So it is not exactly 2, the number you should use to divide. You can use what you can search between 1.99 and 2.01, meaning that that dominant harmonic is not actually twice the fundamental. And if you do that, if you correct using the SVD entropy, okay, you find something like this. Okay, and sometimes you can run an extra step of synchronization, especially useful for these spiky signals with wide bandwidth, okay, especially useful. And you can find these 2 different waveforms. And as you can see, these are premature ventricular bits, exactly. That's what happened here. That's why these bits are different, because premature ventricular contraction, okay? Premature ventricular contraction, okay? Okay? Some same thing for accelerometry data. This was just a guy just ascending stairs and then descending stairs, and he was wearing some devices at at the right ankle, at the knee, also here in the hand, okay? Recording the acceleration in the 3 axes. What you do is you take just the modulus of that vector and you create this signal. Here, I am zooming in 3 parts just to show the difference between these 3 tasks of ascending the stairs, walking and descending the stairs. If you run again, and if you refine, iterating and iterating, always using the SVT entropy as an indicator, you're able to after 8 demodulations with the second harmonic here, you have something which is reasonable, and you find these 3, something like that, okay? Walking, ascending stairs and descending stairs, and the guy just clapped, okay, just to mark the transitions. One mistake here, but I mean, we can all agree that this waveform, it's very different from the other ones, okay? So again, this algorithm was useful to segment the signal and to detect different activities from the for the patient. Okay, that's it. Non-stationarity is not to be taken into account. This is a versatile tool. I think it is a good tool for signal decomposition, denoising, and segmentation. Of course, more work had to be done. And of course, there is room for improvement, and that's what we are trying to do. I'm sorry for the time. Thank you very much.
Thank you very much, Marcelo, for the presentation. And we now open the space for questions from the audience here in the room, and also is there any question in the virtual audience? So please, is there any questions? Please come to the...
Should I go there?
Yeah, please.
Sí, sí, mira la hora que dicen eso.
Thank you for such a great presentation. It was very educational for me. I was not familiar with it, so it was fantastic.
Thank you.
Are you familiar with the work of John Glutak and something called symbolic mismatch?
I'm not aware of that.
Okay, I'll send you the paper. He was doing something that reminds me of this.
Mm-hmm.
He was trying to create symbols in the data, similar to the pulses that you're using, and try to identify differences between pulses and differences in the sequences of the pulses, right? Mm-hmm. So each pulse was associated to a symbol, so by the end of the day, it was a sequence of A, B, A, B, C, A, B. And that's, it's not only one pulse, but also the sequence that...
The dynamic.
Yes.
Yes.
So it reminds me of this. I know the technical details are different, but he was doing this, and I know of this work because he was doing it with ECG, and it was working great. I think he was excited about that, and we tried that in speech. And if you can show the example with speech, I have some questions for you because I'm seeing something that it's a bit weird for me. Exactly this. So for instance, here you have the form and resonance, right? That it's affecting this particular band, which is also seen here, right? Because it's the resonance, I believe, of that form. The person is doing the same vowel but changing pitch.
Yes.
Okay. So when you do the warping, now the amplitude change is misplacing that resonance elsewhere. Is that something you account for in the model with the amplitude constants? How do you? I guess my question is, how do you account for a filtering effect? Is it enough? Is it represented in your amplitude modulation or not?
No, but here, okay. You can see the way you should read this is that this red curve, it shows you the fundamental frequency. And you can see and here everything was just shifted to higher frequencies. Just in the middle part, everything was shifted to higher frequencies. Yeah. So I don't know if you can think that, okay, that's the idea, and what we wanted to kill is to kill that, to have this. But
by killing the frequency modulation,
yes,
you move the format to another position.
Okay.
You know what I'm saying? Because the foreman is affecting this whole bandwidth.
Okay.
It's in this area, right?
Yes.
That resonance of the vowel, right?
Mhm.
The ah, the round 1500. And now you move that resonance.
Yes.
So I was wondering if you're accounting for that change in the filtering effect, that this particular signal is tricky because it has filtering. It's not just a linear model with each one with potential amplitude, but also there's a filtering, overall filtering effect.
Okay.
So I was
No.
just wondering if that's accounted.
No, it's not accounted, but I don't know if in here that's an issue. I don't know how this sound, you know. Actually, it would be fun to hear this warp signal, which I didn't. But no, the idea was just to show that you have two different states. You have low A, high A, and low A again. And if you do not do this, you're not able to detect or estimate these two different waveforms. But there is no analysis of either formants nor filtering. No. And I'm not sure if...
I would say that the changes that you're seeing are because of the filtering effect are affecting the harmonics differently.
Yes.
And it's a natural thing that happens when the filtering
For
and
sure.
baseline is changing. So
For sure.
it's
Yeah.
not, I wouldn't say that it's, I mean, I'm sure the structure is different, right?
Mhm.
As signal structures are different.
Yeah.
But I know how meaningful that change is. And I'm thinking on the clinical things, right? The
Yes.
application. This is just the way the system works.
Mhm.
And I wouldn't say, unlike the other example where you were able to detect something that was physiologically meaningful,
Yes.
I don't know if these particular differences that you're seeing in these clusters
No.
really mean something that
No.
it's meaningful.
No, they just might mean that, okay, you have, I mean, you are able to detect two different waveforms, but anyway, if you analyze just this, you are able also to tell, yes, low, high, low. But since actually I didn't know what to expect here, you know, and as I said, I actually expected maybe this high, but that's because I don't know almost anything about this voice production. So I actually expecting maybe to have in the middle the same as before, but just shifted towards a higher frequency. So that meaning the same waveform, but just here more compressed. That's it, you know. But just because I didn't know what to expect, and then okay, I'm showing you this. But yes.
Okay. So I think when we did this work with Jonathan, he was used to seeing the differences in the ECG signal and identifying just like you did. And when we applied the approach for speech, we had a lot of problems because of this, because you had to do time warping and phase warping and amplitude demodulation. And it turns out that frequency and amplitude are key component. And when you try to normalize everything to pulses, it's very difficult to have meaning. So it actually didn't work as the way we thought, and I would love to revisit this, and I will share the work. Perhaps there's some room for discussion with this.
Please, thank you very much.
Thank you.
Please, thank
Nice
you.
work.
Thank you.
Okay, there is another question, please, Leo. Please, Leandro.
So, just a comment here. So, what happened here is that you so here's the components. You go here.
Okay.
So that's what produces the
Yes. Yes, for sure.
Oh, sorry. Okay. Put the EKG.
Here.
This is a very, very interesting example because last year I had to do some work for an enterprise. Holder segments. And we did almost the same as you, but from another point of view.
Okay.
So we started from QRS detection, so we can synchronize the segmentation
Yes.
once practice. But then we used instant frequency to determine the size of a window. We resample all segments. So
Yes.
it's equivalent to the
Similar. Yes. Yes.
warping.
Yes. That
And we do almost the same for cluster things.
I was not aware of that. The one possible problem with that approach, when you try to extend that approach to other types of signals, that is called a landmark point of view. That you use some landmarks in your signal, and different signals might have different landmarks, and since those landmarks are specific temporal points of the signal, they are more susceptible to be corrupted by noise. And here what we do is we segment the signal, but we do it with the phase. Okay? We do it with the phase.
The problem you have here is that to detect the phase, you have the limit of the
Yes. Yeah.
windows.
It could be,
so
yes.
I see some example. The problem is yes, here. Oh, previous one. No, this one. The problem you have here is that there are small,
Okay.
smaller than your
Yes,
window
yes.
size. So you have two over
It could be, but it is just one.
simultaneously.
You know, this is just one segment of the signal. It's just one here that happens to be here. You know, around
Probably the
90.
high frequency
Could be.
segments that
It could be. We make a comparison to those landmark points approaches, and they might be useful for some specific types of signals. And sometimes, okay, you say, I segment my signal, and all the segments for you will have a different length. But then, okay, maybe you chose the longest one, and you interpolate the rest of them to match that. But then all your segments, they have the frequency modulation information. Okay, all the segments, they are different from each other because they are different wave shape functions and because they are modulated in amplitude and frequency. So here you try to kill those two modulations and focus only on the difference. So that's the extra flavor of this approach. And we try to cover different types of signals, and not only, but yes, in some applications, it could be that maybe landmark points it could be, yes, for sure. That could be complementary information that we decided here not to use because we rely on the model and on the phase and on the warping, but it could be for sure complementary. Try to estimate things. Thank you.
Leo, please.
Thank you, Marcelo. Very interesting work.
Thank you.
I remember an old paper that we wrote with Maria Eugenia and Humberto. I don't know if you read it.
No.
2006, I think.
Okay.
In that paper, we tried to also detect what slight changes using the resolution entropy and self-organizing maps. It's similar idea in some way because we do some type of clustering also, but with these self-organizing maps. Your proposal, I think, is more compact, elegant, more pretty, I think.
Thank you.
But some ideas are similar, and perhaps if you have more than 2 or 3 type of wave shape functions, it is interesting to have this type of map
Yes.
with some metrics of similarity between the websites.
Yes, I understand. Yes, yes. Yes, it could be. I mean, please share with me that paper. I will take a look. But yes, the idea of a self-organizing map is also an idea of clustering, unsupervised clustering here. Yes, yeah, it could be. Yes, it could be. It could be. Okay. Yes, yes. The idea, especially for the slowly varying model, was that those segments, those cycles, they live in a manifold. That was the idea. And when they are changing, you move through the manifold, which is a lower dimension approximation. But that was for the slowly changing model. For this one, we did not mention any idea related to manifold, but anyway, I will take a look at that paper you mentioned, and maybe there is some relation. Thank you. Thank you.
Okay. Is there any other question? Please, one. Which mapping?
The mapping.
Ah,
The
yes,
warping.
the warping. Yes, yes.
So when you got this kind of situation,
Maybe.
when you have this theorem, you are bounded by 5
Yes,
line or
here.
something.
Yes.
You've got 5.
Yes.
When you have epsilon times 5 prime,
Maybe here.
here, for instance, no, here. For instance.
Yes, yes.
So you've got to have this. Okay. So imagine that you got in the last example you have jumps.
Yes.
So in fact you don't have this kind of differentiability.
Yes, that's
so
true.
You are somehow outside of this theorem.
Yes, and
So
exactly, and that is why we commented on that, and that might be one of the causes of why we had to iterate so many times in that example. But for sure, in that case.
And also, what I feel is that you are talking about the dominant component.
Yes.
Whereas what you always estimate is the fundamental frequency.
Yep.
And in the end, for instance, if you look at the last example, one of my concern was, in fact, here, just on the voicing, you will be tempted to estimate that one, not
yes.
that one. Because
yes.
Noise, this one is going to be maybe not detectable, whereas this one would be.
Yes.
So maybe from a strategical point of view, maybe because you are saying, okay, I detect the fundamental frequency, and everything is based on this kind of thing, right? And if, for instance, it is not detected or with errors, then you are going to, even if you've got some jumps, then you are going to have this everywhere because of the model, warm stars. You have this jump that propagates throughout the harmonics, right?
Yeah.
And so you are going to try to find something. So I was just wondering if it's the
here what I mean. You can either use the fundamental one or the dominant one. The rich detection algorithm will go for the dominant one.
Yeah, but the thing also is that the dominant one may be dominant for one time, but
exactly,
not
exactly.
You see that
yes. But in the model,
you have to have one, but then maybe the other.
Exactly. You assume that the dominant is the dominant for all t. But if you want here, and what we did here, if you want here the fundamental one, you apply that D-shaped algorithm that is just a short time Kepstrom transform. And you will find this red one. Otherwise, you will find this. But that.
In fact, that's a bit the same question as he was asking. But dominant one here is dominant, but you switch from one mode to another.
Yes.
And so you are not in the same case. You can't have this hypothesis. So,
yes. No.
So in fact, that's why maybe in the end you end up with some jumps in the amplitude that you are not taking into account. You are assuming it very slowly.
No, slowly. It should vary slowly only for the dominant or the one you consider to be dominant. Here.
Yes, but you see here, since they are not.
Yes, and yes, but that's the idea that here you have varying amplitudes that explains The,
Right, that you're not going to go there.
no, explain that in the third model, explains these changes. As you can see here, the other harmonics are almost exact multiples. Okay, so the modification of the wave shape, which is the thing that I want to estimate, is caused by this change by these changes in amplitude.
Yes.
So it is okay. It is okay. You are still in the model here. That's the idea. In the third model, okay, in the third model, in the V3.
Yes, because we assume that the damage varies for each.
Yes, for each.
And,
But here, why this works okay with the fundamental, and there is no need for the dominant. It is because of this. It is because for each time you have an almost perfect harmonic structure. So it would be the same. That's why it does. You don't need to iterate here, okay? But and there is no noise here. But if you go,
the meaning of the
if you go here, yes, sorry, yeah.
You see that the amplitude will be translated by the fact so that we are creating shapes, wave shapes.
Mm-hmm.
That are related to the amplitude.
Of the this is also divided by this amplitude, okay?
But it seems almost constant.
No, yeah, but it is not constant. But here, since it is divided, it is constant.
Yes, but then you see that the ratio here are different because that is propagating somewhere.
You have a different wave shape here than here.
Yeah, so my concern is that I think that the wave shapes are different only because of the amplitude.
Of the amplitude of the harmonics, yes.
Yes.
But that's the model.
Okay.
They might also be different because of the non-integer multiples.
Okay.
But for these three,
For this case, it's extremely amplitude.
for this third version, V3, it is different because of the amplitude of the harmonics, and we allow the model to do that, and we want it to detect. Every time we want to go to a spectrum like this, with almost constant frequencies, and the dominant or fundamental, depending on your choice, almost constant. But this is, as I said, this is a very easy example to do this, and we estimate these two. And of course, the interpretation of this estimation, as Matthias said, it is logical for the people from the voice field. But in this case, you see here, if you demodulate and warp and demodulate, I call demodulation to the division with the amplitude. If you demodulate, you find an almost constant at the frequency 1, but the rest of them, no. And also the noise content on this harmonic should be greater than this one, because you have more energy here. So you have this. And you can see the higher, if you segment this, of course, you can expect this, because there is no harmonic structure.
Because in the electromagnetic, we know that the fundamental frequency is not the one.
Exactly. But if you do with the second one, you see, and this is what you want before your segmentation, something more like that, as opposed to this. But there is an idea of why you should demodulate or warp with the dominant rather than the fundamental.
But what would be depending on the choice for
yes.
What waveform will you obtain?
Yes.
That is, if you change the initial guess, does it has an impact on the waveform?
It does impact.
So in fact,
it does impact. It does impact. Actually, this is the idea of okay, I got this idea. We will use the second, which is the dominant, because it has better signal-to-noise ratio, and we speculated that the dominant would carry the most information. That's just a speculation. But after I met Ingrid there, we discussed some ideas, and actually, this might not be the best one to estimate. Okay, It could be that the fourth one might be the best. I didn't try. The fourth one might be the best because even though the amplitude is smaller than the second one, since here when you divide this estimation by 4, you are dividing the noise content by 4, okay? That's what we talked yesterday, I think.
Maybe your estimation.
While driving.
You can just try to find out the times where you have the harmonicity.
Mm-hmm.
So depending on time, you could say, okay, at that point I've got the harmonicity, here I've got noise.
Mm-hmm.
So maybe you could just raise your wave shape.
Yes.
So only, not on all the time, but on the points where you have quasi harmonicity.
Yes.
Because here you are going to take that into account where there's noise.
Yeah, but there is not too much noise, you know.
Yeah,
Actually,
there is
yes, but this is because it is a different wave shape function. You see, at that point, at that time point here, you have a different wave shape function, okay, and that's you have here, and then you have ta 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 here. This is the original time between 10 and 12. Oh no, this is around 20. What happens around 20? You have this, okay? And you have a different. This, yeah, I think this is the original time. Okay, and you have that.
Okay, so
you have different behavior. Yeah.
Last question.
Mm-hmm.
About when you have a sum of cosine, and at some point you add some sine.
Yes.
In your model.
Yes.
So in fact, you always have a.
Yeah, no, just to add a phase shift, just to add a phase shift.
Yes, but in your model you don't take into account that operates at a sum of cosine, right?
No, but you have I think. Well, let's return.
I don't know how you can take into account a phase shift.
Okay.
Just in your model, you have always a sine, right?
Yeah.
And in your example, at the beginning, you had sine.
Yeah, but this is this 5L. It
can have a constant.
It can have it can have
a
constant shift. That's the idea. But this is the big 3.
Okay.
And
But
you
here,
you see, no, you do not estimate the BL. And non-linear regression, but if you, it's taken into account when you estimate this guy, we have the alpha and beta. Thank you.
Is there another question from the audience? Is there any question from the people? So, Marcelo, thank you very much for this.
Okay, well, so we are finishing now. I'm sorry, guys, for the. I was 5 minutes late. I'm sorry. So this is it, I think. Thank you, those of you who join us around the world via YouTube. Okay, this is the end of the first edition of the workshop on advanced signal processing, machine learning, and modeling. We hope just for it to be only the first edition, with many more to come, also in maybe in other countries, but other countries with an ocean view and with that kind of things, you know, maybe across the mountains would be great. Thank you very much. Gracias por estar acá. Muchísimas gracias. Así que gracias.